I'm not gonna remember. I'm not gonna remember the title. Okay, there it is. You good? Okay, so I think we're gonna get started. Yeah. To the 31st of the US Computability Seminar. Let's see everyone here. And our first speaker will be Peter Cholak. I don't remember his full title, but it's about computability theoretic aspects of results attached to Dobrinen.
Very good. So I wasn't planning to write, I'm going to give a Blackboard talk, so you have to bear with me. So the title is some computer theoretic aspects of Dobrинen's proof that, well, the ultra homogeneous triangle free graph has big Ramsey degrees. So I'll make this part, we'll go through this. So we're dealing with graphs. Well, without triangles. Oops, I drew a triangle. Okay, so I obviously failed initially, but we don't want to have triangles. That's a no-no. Okay, no triangles. Okay. Now I will say that is what I just drew there was a 3-clique. And so what I also kind of has to do sort of applies the graphs. So this I'm looking at graphs that avoid. So graphs avoiding and it could be also the end clique, but I'm not really going to say much about it. The combinatorics is different, right? So that it's doable. All right, and so let me this is a Ramsey theory talk, so let me actually set the main discourse I'm looking at here. So I'm looking for a unique graph that's countable. So well, countable. It's going to be not finite in a second. We'll see why. Can everybody read my writing? I'm going to change it to black. Also, it's going to be triangle free. Also, and now this is a property they want to have happen here. So for all D, so D will have no edges. All right. So when we're looking at a graph, we have a vertices and edges. So our vertices here will be somehow some countable object, which we'll think of as omega, and the edges, right? So D is a subset of vertices of our nodes, and I want to be completely disconnected. So I'm thinking of as an edge as a connection, right? So that means pairwise, there's no edges in between these vertices, and this is finite. All right, and then for all F, again, finite. I don't care if there's edges or not. Because we're working in this triangle-free graph, there's no triangles in these vertices, okay? And now what I claim is that there's a vertex V. So V is basically, I'm gonna write this V is connected. I got it. Connected to D. So I'm gonna write it like that. V is connected to D. So I mean, really, if you have V, there's a whole bunch of things in there. Each one of those is connected to that object. Okay, and then here's F, whatever it is, and it's not connected. So I could, since I have colored chalk here, I could write it in red. There's no edges between them. All right, so basically for every D that's completely disconnected and finite, and every F, I have this extension. Okay, and so that's enough to actually describe this graph. Right, so this graph, so this is the graph, which I'm going to call H3. So it's countable, right? Because it's not finite, right? Because I keep on extending and extending, stuff like that. Okay, and so this is the object I want to look at, H3, and there's of course the HN we can talk about. All right, so
just to be clear, D is connected to V and F is not connected to V.
Yeah, so here everything in D is connected to V.
But nothing in F is
nothing in F is connected, right? So maybe I should write that out. I mean, for all little d and capital D, there is an edge between D and V. And for all little f and capital F, there's not an edge between F and V. So this means connected, this means disconnected. Okay, so when I say the words connected and disconnected, that's what I mean in this context. All right, so we have an idea what the graph is that we're looking at, H3.
And when you say H3 is unique, you mean it's homogeneous or something?
Yeah. So any copy I have of H3, right? And anything that satisfies this, there's gonna be an isomorphism back and forth between them by this property. Just go back and forth. Right?
If you just write those part two sentences down, I have no particular reason to think that it's fallacy.
Triangle free, countable, and has this property.
Okay.
You just,
Okay, right, so you're just saying there's something like the counter argument.
yeah. So back and forth.
Okay.
Back and forth, right? Just back and forth.
Okay.
Right, if they believe that, because that's important. Right, so if I just do a counter argument, right, so I'm just saying, I mean, this is homogeneous. Right, we know the argument that homogeneous structures are, that have the same types are kind of or isomorphic, right? So this is the same thing. Okay. Are you okay, John?
Yeah.
Okay. All right. So so that's the object here. So now let me talk about what it means to be big. All right. Big. Okay, I gotta write this right. I gotta get in trouble. Oh, by the way, this is joint work with Natasha Dobrinen and Charlie McCoy. And I'm a terrible speller, so I make sure I spelled the names right. Did I spell her name right? She might be watching, so I better make sure I did. Nope. Got my letters mixed up. Okay, so anyway, this is joint work with Natasha and Charlie McCoy. So Charlie McCoy was an old student of mine from many years ago. He was visiting Notre Dame over the summer. Okay, so all right, so I want to talk about what it means to be have finite big Ramsey degrees. Okay, degrees. Okay, it says for all B, a substructure of H3. Okay, so B is a finite substructure. So examples of finite substructures are just nodes. Right, it's the node. You can also have a pair of nodes that are connected. You could have a pair of nodes that are not connected. You could have, say, 3 nodes which are not connected. Right? I mean, in fact, the whole thing I drew is one of those things too, right? I mean, so I didn't have to, this was one, this was another, this is another, but the union of everything is also a substructure with the inherited substructure. All right, so this says, so there exists a T. Okay, now it says for all finite colorings of B within H3. So I have, so there's lots of copies of B inside of H3. Okay, so let me just show you one quick argument like this. So I haven't really talked about H3, but I have some finite piece of it, right? I can always kind of copy B by using this extension principle bigger than what I had done out there, right? So there's lots of copies of B within H3. So if for all finite copies of B, so we have a finite, so yes, for all finite colorings of B within H, all right? There exists copy H3 tilde of H3. So I'm getting this is where the big comes in. I'm basically getting a copy of my original structure, right? That's what I want. If you're looking for Ramsey theories, really it's homogeneous, but this is what I want. It's going to be a copy of this, right? Where at most key colors are used for copies of B within our copy H3 tilde. Okay, so basically I got a coloring, right? This is the result. So I color my triangle free graph, right, by some B. So let's just, so by the way, this would be the nodes. This is edges. This is non-edges. right? This is not K3, not, completely disconnected graph. Okay, so I'm saying is if I color my nodes with, 5 colors, right? I get some coloring where I have just 2 colors, okay? And we say that if exactly T colors are used in this copy, right, then T is exact. Okay. And so this is true. This is a theorem of Natasha Dobrinen, right? This is what she proved. Okay, so I'm not going to reprove this today, right? So, but all I'm saying is in this is here that any coloring we have, pick some copy B, edges, nodes, whatever you want. Color B, there's some T, which I'll talk about in a little bit. So it's that for any coloring I have of B, right, I get this copy, right, where I just use T colors.
Is the copy sitting inside H3 that we started with?
Yes, yes. So this is inside H3. Right, so it's I've already colored it. Okay. Okay, so I'm going to use this. I'm going to use, pieces of this, but now let me tell you what our results are. Okay, so I'm going to erase this over here. Okay. So I'm going to kind of go, well, first I'm going to focus on nodes. All right, so that's just an object there. Here, T equals 1. All right, so by the way, let me back up here. I want to call this copy here. I want to give a name to this copy. Okay. I'm going to call this the minimal heterogeneous copy of H3. Okay. Or minimal heterogeneous copy of that. Okay, so
I think there's a question in chat. So it's only copies of B that use at most T colors, not all of H3 tilde?
only B. Inside H3, the copies of B use T colors or less.
Thanks.
Yeah, so most T colors are used for copies of B within this copy. Okay. And then if T equals 1, I'll call this the homogeneous copy. Right, so I have this new name, minimal heterogeneous copy, right? It's a mixed copy with the minimal number of elements. Okay, and so so here I'll just point out here, I want my colorings to be computable. So the object I talked about is computable, so I want the colorings to be computable. And the question really here is, what is the Taurian degree or Taurian degrees of minimal heterogeneous copy? That's what we're kind of, that's what I want to answer. Okay. All right. So let me write down the results. So T equals 1. So sorry. Nodes. T equals 1. All right. So I'm going to use this, but there's actually a result of Gill that there is computable coloring where no homogeneous copy is computable. Okay. So by the way, so I'm not gonna, this is a new result of Gill, Kenny Gill, who is a student of Linda Westreich, and this could be found on the archive too, if people are interested in looking it up. We'll talk a little bit more about that in a bit. Also, and I was supposed to write down the names, but I don't know, I have my grandson's living with us, and so I was told to hold him when I was in the middle of writing my talk. So I forgot to write down the names. But for all colorings. So again, I'm saying computable colorings. Basically the homogeneous copy can be found below 0 prime. Okay, so you can always find a homogeneous copy below 0 prime. I assume everybody knows what 0 prime is. This is a computability seminar. All right, now, so I will say that there's a question here. I'm just gonna ask this question here. This is still unknown here. So for all colorings, they're computable. For all x greater than, Taurian greater than 0 prime, right? Does there exist does there exist a homogeneous copy such that the copy H3 avoids the cone above H? So this is cone avoidance, right? So in other words, this is still open whether this satisfies cone avoidance, right? So well, we know we can find it's not computable. We don't know if it satisfies cone avoidance. This would be the next step in kind of analysis that's going on in this object here. All right, so that's what happens with nodes. All right, so let's do pairs. All right, so pairs, sorry, edges. So edges t equals 2, and I'm going to try to show you why t equals 2 later, okay? And here we have basically, there is a coloring. I'm going to call it a jockish coloring, because I think Carl's here. Such that every minimal heterogeneous copy computes 0 prime. All right, so there's a coloring of edges such that if I'm looking for any minimal heterogeneous copy, computes 0 prime. Okay. Now here's a question that I don't know how to answer yet. So the question, this is the simplest question. Is there arithmetic minimal heterogeneous copy? So I don't know how to prove that there is a minimal heterogeneous copy at all at this point, right? So I don't know if this thing is arithmetical or not. Now we know that there is actually one below 0 to the mega by results of Ludovic, by Pate and other people, and a different proof. So I'm not going to go there. So we know it's just above arithmetic, but we don't know if it has to be arithmetic. Okay, so that's an older result that you could find on the archive also. All right. So all right, so I want to hopefully show you this, right? Why I'm calling this jockish coloring. Look at that. Now non-edges. All right, t equals 5 for non-edges. So I can't count that high. I could go 1, 2, 1, 2. If I add those together, let's see, 1, 2 plus 1, that's 4, and then just a little bit. So I think that's all I got on my hand, right? So I can't go any higher than 5. Okay. So, but once we get an idea of what happens with 5, we're in good shape, right? So here, you know, we get this result here. Okay. Once we have, right. In fact, what we have is for all b, where b has size greater than or equal to 2, we get this result, right? Any minimal homogeneous copy code 0 prime, but we get a little bit more. Okay. So the other thing I want to do, we'll get there, we'll see this here. So let me erase. The other result I have is the other result I have here so well, this, okay, so I want to show you this implies Ramsey's theorem. So, but let me try to be a little bit more specific about that, right? So I want to pick out, so I want to probably prove this, say. Right, so maybe this is, you're coloring n tuples of the net rationals with k colors, and you get a homogeneous set of size 1. Right, so I'd like to be able to prove why this is true. So what I'm going to look at is not this is so not kn. So this is the completely disconnected clique, right? This is a subset of H3. I'm not going to tell you what the T is for this. All right, but what I'm going to claim here is that every I could code this in such a way, right? I could color this in such a way so I could color. So basically, I'm going to say given coloring of the n tuples of omega, right? We get coloring of B, K, and inside of here, such that all minimal heterogeneous copies code homogeneous copy for the coloring I have on omega. Okay, so that's enough to get a lot of information, right? Because we know a tremendous amount about what happens with Ramsey's theorem, right? So that's enough for all kinds of stuff. Okay. All right. Questions? Okay, let's see where I am. I did prepare. Isn't that good? All right. So now what I'm aiming for is just try to prove some of these results, right? It's actually not hard if you know what to look for, right? But of course, with everything, it's figuring out what to look for, right? That's the hard part. Right, so I'm aiming for edges. That's what I'm aiming for. Okay, and then, if I can, I'll get to this. I'll say something about Gill's work along the way. Okay, so we're doing aiming for edges, talk about nodes along the way, and then we'll also talk about this anti-clique. Okay, so let me erase. All right. So first of all, the structure I'm looking at is the structure I'm looking at. This is countable, right? So I'm going to pick a numeration of this. So somehow, E0, E1, E2, ... right, and edges. I'm picking this like this. So I got some enumeration, right? It's countable, right? I'm told it's countable, so I have this counting, right? I'm gonna need this, right? This is kind of interesting. Now I want it special. I want to modify this. I want to get a copy of H3 such that, well, I want it to be, it's gonna be A0, A1, A2, so on and so forth. Again, and edges, but these are different things, right? Kind of my non-right, right? But I want basically there is an edge between. I want there's always, as I enumerate the element, it's connected to the previous element. Okay. This I want a special property. So I'm gonna do this stage-wise. So I'm gonna basically. So I'm gonna do a stage-wise construction of these AIs. Right, so I have this enumeration I've given. I'm going to do the stage-wise construction. So let's see. So I have to make sure they're isomorphic back and forth. So they have to preserve the edge property, right? That's the only thing we have to do, right? So I have something so far. Well, let me put the A's on top. So I have A0 up to some AI, and these are isomorphic to E0 up to EI. Okay. Now, if I get so lucky that EI plus 1 is connected, right? Then obviously I could just do that, right? Is that good? John, you get to be the goat.
Right, yeah, that's easy. Now what happens?
Oh, the other case. Okay, the other case. So the other case, I'm gonna put a little space here. So we have EI and it's not connected, right? So I can put, there's no connection. But now we know there is something that, so there's no connection. So we know there's something that's connected to both of them, right? My extension property, right? So there's something there. So it's just some E. So I'll just put, you know, this is EK, whatever, EK. So that will be AI plus 1, and then I'll have this next one here will be EI plus 2. Okay. All right, great. Okay. Maybe I skipped a second. Okay, so now I want to talk about, so now this is my enumeration of A. Okay. And now what I want to do is I want to define a neighborhood set. What do you think it is? Things that are connected to me, things that are neighbors to me, right? Right, so there's the neighborhood, but I want to be a little bit careful. So N AI really is a set of J greater than I, such that basically there's an edge from AJ to AI. Okay, so there's an edge there, right? But I want one more piece of information. I want to have, and for all K less than I, there's not an edge between AJ and AK. Okay, so so now think about this, right? The point here is that in this enumeration, this is connected to the least thing before, right? So what neighborhood set does it go into? It goes into the least thing it's connected to. Right, so we're doing exclusive neighborhood sets, right? Because we all live in exclusive neighborhoods, right? Right. So now I'm going to draw a picture the way I like to think about this. So I'm thinking about so these are my neighborhood sets. This is the first neighborhood set, the second neighborhood set, the third neighborhood set, right? And they're all disjoint, right? Because once I'm in one neighborhood, I can't get into another neighborhood, right? Okay, and everything in each I goes, so I have that basically, you know, I have that H3 is contained in this disjoint union over I of my neighborhood sets. Okay, and so I'm thinking about so I'm just thinking of neighborhood sets going up this way, and I'm thinking about I going up that way. Okay, so neighborhoods up the way. Okay, and I should point out here that AI is somewhere as an element of the disjoint union for J less than I of the neighborhood sets of the AJ. So in other words, if I'm looking at this, you know, if I'm looking at the ith element, right? So if I look at where the ith element is up here, so this is up here, I, right? It's got to be somewhere in these neighborhood sets. So it's not up high up the spine, right? So you might call that the spine, a bunch of zeros. Okay. Okay. All right. Okay. So now I want to prove something about this. All right, about my neighborhood sets. So first, there exists, not over there exists. There exists some collection of vertices in subset of H3. Okay, and so H3 maximal, and it's going to be computable, so it's maximal with respect to what, so it's computable. Such that really for all nodes in these set of vertices, there exists a unique I, such that basically N is in the neighborhood set of that AI. Okay, so right, so everything is in one neighborhood set. There's only so, and I should really say that so if I'll write this AI intersect V, the size of this is less than or equal to 1. Right, so I have one element in each neighborhood set. Okay, and no edges. Okay, so I claim there's a maximal such one. Well, let's just see here. So let's just start, right? So I should be, this is here, this should be here for, this should be for all copies of H3 inside H. So in other words, I want to be a little stronger than this. Not just inside of H3, but if I take any copy I have, right? However, any copy of H3, however it lives in here, right? So I haven't told you how a copy of H3 could live in here, right? So I don't know, I'm not gonna even talk about it, but there's some copy, right? That's a copy somehow of H3, and I want to see how it lives in there. So I claim that inside there, I could get something like that. So let's see how we do this. So inside H3, I have, so I want to prove that I could always get it do this. So I have some elements here. They're disconnected. Okay, now I get by my extension property, there's another element that's connected. Oh, by the way, so I have another element that's connected to each one of these, right? So I need one fact I should have mentioned earlier. Can I have an edge in a neighborhood set? Just think about it. A neighborhood set is about a bunch of things that are connected to that, right? So if I have two objects that are in there, and they're both connected, they're both connected to the guys that form the neighborhood set. So basically, no neighborhood set has an edge. Right? There's no edge, it's edge free. Right? Unlike this talk. Okay. All right, so it's edge free. Okay. So, all right, so that means I want to get something that's connected. There's some object that's connected to all three of those, right? It can't be in any of these neighborhood sets, though, right? So I've got something that's connected to those objects there, right? Now this doesn't do this property here, right? But this is in some neighborhood set, right? Now this is in some neighborhood set. Now, by the way, so if we don't this is in this neighborhood set, and now what happens is I want to find something that is connected to this object here, right? To this one. Connected to this one, but disconnected to all my original ones. That's fair game. Right? And so that object is what I want, right? Right? So I can keep on going all the way up and get this, right? Copies all the way. Right? So I could get well, so it's going to be size of, okay. So one result we get out of this is that no copy of H3 lives in finitely many neighborhood sets. So every copy you have must hit infinitely many neighborhood sets. Okay. All right. Now, okay. Now I'm going to use the result that basically H3 is indivisible. I'm not going to prove this. And this says that if you basically two color the nodes, there exists a homogeneous copy of H3. Right. So if you two color the nodes, you can get this homogeneous copy. Okay. All right. Okay, so now, all right. All right, so now, okay, so I'm gonna use that. So that's one result. Now I'm ready to talk about edges. So those are results I need. I know what a neighborhood set is. I know no copy lives in a neighborhood, in a finitely many neighborhood sets, right? And I have this indivisibly result. Now, so let's think about edges. All right, two nodes in an edge. They're in an edge. They're edgy. We agreed they can't be in the same neighborhood set, right? Okay, so I'm gonna label them, so we have I and J. Now what happens is, so they're in two neighborhood sets, right? So I'll put, so and I want basically I less than K. Now this is in some neighborhood set. Let's say this is in the Jth neighborhood set, and this is the Lth neighborhood set, right? Could be like that, right? That's reasonable. Right now, so this is, I'm gonna be nebulous A, K here. So let's see how we can arrange these edges in this way. Right, one thing we know here is that AI is connected to AK, right? So that means that, and so what we know here is, well, first of all, we know that J is less than I, right? Because I gave you that nice ordering. Right, that was important. But now also L is less than or equal to I, right? Because this guy, AK, is in the least neighborhood set, so it's connected to AI, so it's got to be in that neighborhood set, unless there's something smaller. Okay, so we have that, and so we also have that I is less than J, but that is all we have in terms of the possibilities. So there's only one, that's all the possibilities. So let's see what these guys look like. These edges look like. So what I'm going to do is I'm going to relabel this node here. I'm going to relabel all my nodes here with A, J, I, and this is basically A, I is in the Jth neighborhood set. So I get an extra indexing for each node. So I have two indices for each nodes, an I and a J. Now let's see what happens with these edges. So here are the edges. Okay, one of them is bigger than the other. All right. So I'm going to just tell you the configuration. So I'll just draw them here. So this will be a I, this will be a K, and this will be the L, and this will be the J. Something looks like that. Right, that fits the bill, right? Right, so I have, right, I is smaller than K, J smaller than I, right? And there's, the relationship between this is supposed to be a J, between J and L is unspecified, right? So it could be like that. Or another way it could go like this way. AI, AK, and this is J, and this is L. And you think about it, there's no other ways that you could draw a pair of edges inside these neighborhood sets. That's it. That's all you could do. Right? They all have to live in a different neighborhood set. Right? Well, so you can flip them. Right? One's bigger than the other. That's it. Right now, I want to focus on this one here in particular. And I want to color it. So I want to color this one. So this one I'm going to color like this. So I'm going to color this. So now if I have a pair of nodes, right, there's 4 indices involved, right? So I'm allowed to color this using these 4 objects, right? But I'm going to use 3. So I'm going to just say, so I'm going to color this blue. This is the Jockish coloring. If I have K up to J at stage I, so is equal to K up to J at stage K. Right, so this is blue and it's red otherwise. Okay. All right, so now what I want to show is that when I look at this object, that I get basically, I want to show that the color I get of all these objects is always blue. Because these are my 2 types I have here. These are the 2 types. They're different from each other. So I could color this one different than I could color this one, obviously, right? So if it looks like this, I color this, fuchsia or purple or whatever I want. Okay, so I get a color here for this object and a color for this object. not gonna prove that, but that's what happens. I get a color for each of these objects. So now I just have to show that when I get done, right, that on the homogeneous copy, it's blue, and this allows me to compute zero prime. Okay, so let's do that. So now I'm back to my copies of this thing here. Right now I get a copy. I get a copy of H3 where these types are the same. And it's one color, and these have one color. Those are the two types I could get, one from each of them. Right, so I get a copy like that. So I'll put it in red. It's somewhere, you know, it lives like that someplace. Okay, it's not everything. Right now, I know I'm going to start using some. I want to show you that I get the right color. So I know that well, it can't live in finally in neighborhood sets, right? So, but I know that the first there has to be some node someplace, right? Somewhere that's hanging out, and there has to be a neighborhood set for that node someplace, right? So let's just figure out where that neighborhood set is. So there's my first node, and that's the neighborhood set I'm after right there. Okay, now let's cut it off up there. Okay. Okay, now I know I got another copy above that part. Inside the orange, I have another copy of H3 above that part. Okay, so now I want to live above that part there. Okay, so I have this. So this will be so there's some level L. I want to be, did I use L? Let's call it M. All right, so I'm above that. I want to be above that level, but I know that here I have a neighborhood set. And by the way, once I'm in a neighborhood set, one thing I should point out, the neighborhood set is infinite, right? The neighborhood sets are infinite because if I want to be connected to this, and I just, I want to be connected to this, and I want to be disconnected to all these objects, I could do that. So the neighborhood sets are always infinite, right? So that's a lot of stuff there. Right now, I'm ready to go. So now I'm just going to pick. There's got to be some next neighborhood set. So I'm going to do the same thing. There's another neighborhood set out there like that, right? Infinite, right? So this will be my first. This will be J, and now I'm going to pick this so large because it's infinite that we have that K, right, restricted to J. Whatever this is equal to basically little k restricted J. So I picked that so big out there, right? That's so big that it doesn't change, right? I can find it's infinite. So I got something way up there, boop, and then I'm gonna pick out here. This is I, and then I'll just pick something bigger than that over there because that's infinite also. So I got it blue. So I know that the color has got to be blue. All right, now I just have to show that I compute zero prime. Well, I kind of did that argument already. Okay, all I had to do is, and now I just have to pick out a pair out here. So if I want to compute K up to some X, well, I just pick something bigger than X, something here, right? And I want to pick something, and I want to pick a guy that lives out here like this and this. Now I know that this guy's going to be and then if I just pick any other thing that goes with it, all right, I claim that's blue. All right, and this is tricky because it's not blue. Well, that means that K changes in this interval. Well, I just go down here. I go forward the whole way to witness that change on this down here. So I can witness a change, and that will give me a red node. All right, so that's, is Carl there, Dennis? Yeah. That's it, that's Carl's proof. Hopefully I did it justice. All right, okay, now, so I gave you an idea why edges code zero prime. Now look, non-edges. The non-edges, okay, so non-edges, okay, so I'm gonna count. Once I got them in the neighborhood sets, I didn't need to know that there was an edge between them or not, right? I just needed an argument that there was these guys, the edges had to live in different neighborhood sets, right? But I also can have nodes which are not connected live in different neighborhood sets, right? Right, not all of us are connected and we live in different neighborhoods, right? Okay. So, right, so that gives you two of the types right there, right? The same thing I did for edges, I could do not for non-edges. Now, okay, so now there's another type. Remember that these guys were connected. So that means that this guy had to be at least in this neighborhood set, but if they're not connected, you are free to do what you want. You don't have to live anywhere near this guy, right? If you're not connected, you don't have to be, that's the only thing about connection is that we use that you had to be close, right? So now, if I'm not connected, I could go wherever I want in terms of my neighborhood set. So edges, so I got two here. I got one here where I'm like up here and I'm going to be here. And then I want to be way the heck up over there, right? Disconnected. Okay. And so by the way, this allows me, so now this allows, I'm running out of time. This allows me to color Ramsey's theorem for pairs because I'm going to put everything, I should have said this. I'm just going to color everything who's in this neighborhood set and this neighborhood set, regard of edges, just one color. In other words, the color of anything that looks like this depend on just the coloring I have of pairs. Right, so I'm just coloring the neighborhood. That's a neighborhood set color. Okay. All right, so that's another type. So I've got two. All right. Oh, what else can happen with edges, non-edges? Where they can live? So I got three. They could live in different neighborhood sets. They could be like really far away from each other in different neighborhood sets. Or what's the other option? In the same neighborhood, right? Okay, in the same neighborhood, it actually turns out there's two possibilities, right? And so that depends on, because they're not gonna, they have to be, there's some node out there that they're different. There's gonna be something that's connected to one, not to the other, right? So that at least tells you where that gives you another two types. Okay, so someplace out there, I'm in the same neighborhood set, right? But I know I can extend them. Right, so there's something connected to one, not to the other, right? So that least object tells me the second those types. All right, and now, okay, so I'm running out of time here, but now I've got everything I want, right? Because this tells me how to code Ramsey's theorem, just completely disconnected. Every copy of B, whether it contains an edge or non-edge, has something that looks like this inside of it, so I could get a coloring. I can use the Jockish coloring and do different things like that. Okay, so I'm gonna but what I don't know, and I haven't done any proofs here yet about is how do you find these copies, these minimal heterogeneous copies? But that will be it for another talks. That's why I'm gonna come back. In fact, I come back every year, every semester. So, all right, thank you.
Are there any questions, Peter?
No questions?
Anyone in the?
Okay, so then
Any questions, Peter? Okay, well, if not, let's thank Peter again. Well, the copies